Okay, so I'll be talking about optimal transport. And this is part one. And so here the goal is to recall some measure theory, basically. So, um, so it's going to be pretty standard for people who've seen measure theory, but if you're new to this, then perhaps you need to just look at any standard book, and that should work. Um, so let's probably start with a remark. And the remark is so the thing is, optimal transport will be done on a space, and the space that we'll be working on, the space X, we assume uh, it to be separable, complete, and locally compact. So of course, these are just sort of simplifications that you make in order to make the proofs nice, but you don't need to do that. And of course, if things sound too complicated, just think about all the usual Euclidean space. Um, and so now with this, we can have a first definition, at least. So the object that we'll define is called the push forward measure. Push forward measure, and the ingredients to construct this object are just two things. So what you need is a measurable map T that goes from X to Y, and a probability measure mu that's defined on the space X. And so with these two guys, you can define a push forward measure as follows: so T sharp of mu of A. So it's a probability measure that lives in the space Y. So that's the sort of the interesting part about this, is that with these two guys you can define a probability measure on the target space, which is Y. And so in particular, what it must do is as follows. So when you take a Borel set A so you take a Borel set on the space Y, the way you compute the measure of this guy is just by taking the measure of T inverse of A. So perhaps a picture would be helpful. So you have your space X, and then you have your space Y, and let's say you have some sets A here. What you can do is you can bring this back using T inverse, and then you get some sets here, which is T inverse of A. And because mu is a measure on the space X, we know how to measure these sets. And of course, because T is measurable, its inverse image is a set, is a set which is contained in the Borel sets, the space X. So mu can measure this guy, and that's it. That's the value that we assign to our push forward measure. So this is the first notion, and so it would be nice to, just to verify for sanity check. I mean, so the thing is, in the definition, usually this fact is not included, right? You just say that you have a measurable map T, and you have a probability measure mu, and with these two things, you just define a new measure, and a priori you don't assume that it's a probability measure. So technically, we can get rid of this if you want, but as a sanity check, you can prove to yourself that this is indeed actually a probability measure. So depending on what books you read, you might want to verify. So verify that that the push forward measure is indeed a probability measure on the space Y. So of course you can walk through all the steps to check this, but just a quick sort of sanity check. Uh, so we know that the probability of the set y should be it should be 1. I mean, otherwise it doesn't make sense for it to be even called a probability measure. So let's just compute that at least as a basic step. So the push forward of y is simply mu t inverse of y, but then this guy, the inverse image of the whole target space is x, and since mu is a probability measure, we know that this is equal to 1. So this is just a quick sanity check that, indeed it is a probability measure. Otherwise, I mean, what would we care to define it? And then you know that the inverse image, look at the definition, the inverse image is compatible with, countable unions. So it kind of makes sense that we would like to use this instead of the forward image, which is just, let's say, T of A. You will notice once you start proving things about this that it won't be compatible actually with unions and intersections. That's one of the advantages, and in measure theory you come across a lot with this idea of taking inverse images rather than forward images. So now what you can do is we can prove something interesting about these guys. So let's state a lemma. And the lemma is that let t be just a measurable function going from x to y, and then you have mu, which is a probability measure, and then nu is a probability measure on the space y. Then there's a criteria that allows us to check that nu is actually, if nu is indeed a push forward measure. And this criteria is pretty simple. So nu is a push forward measure of mu if and only if for any phi that goes from y to r, so any such map, which is of course Borel and bounded, so it's measurable and bounded. We have that the integral of phi y with respect to the measure nu is the same as the integral on x phi of t of x d mu of x. So notice that there's this composition happening, and this is one of the standard properties which characterizes the push forward measure. So when you want to integrate over a push forward measure nu, then you just compose the function that you want to integrate with the map t, and then you're done. So this is not that hard actually to prove. So this is the lemma. I'll go to the next page, prove it here. So the proof is not that hard. So let's look at the forward implication of this first. So for the forward implication, so what we want to do is we assume that nu is indeed a push forward measure, and we want to verify that this claim holds, right? This is actually this one's a little involved. Perhaps I'll start with the easier case, which is actually going backwards. So we assume that this integral equality holds, and we'll show that it is indeed a push forward measure. So to show that two measures are the same, what you have to show is that for every Borel set on the space y, these two measures give the same value. So it's very simple. So you pick, so let A be an arbitrary Borel set. Then what you can do is choose phi to be the indicator function on A. This implies, so now we just plug this phi in this integral equality, and then you get, so you're integrating the indicator function of y with respect to this, and so this is simply the measure of A. But then if you compose this with t of x, then this is simply the measure of t inverse of A, right? So remember that the indicator function of a set will equal 1 if and only if that value lives in the set. So all the tx must live in the set A, and that only happens for all the x that belong to the inverse image of t inverse of A. So that's pretty much from definition. So this implication is easy. So now, of course, the reason we can conclude is because this guy is equal to this guy, and this is precisely the definition of the push-forward measure. So this implication is okay. The forward one, a little bit of work required, but again, not too hard. So what do we assume? We assume that this holds, and we want to verify this for all measurable and bounded functions. But this is not hard. Usually for proofs like this, you follow a sort of density argument, and so you start with simple stuff. So you start with just indicate the function. So we prove first for phi, which assume the form this. So we'll assume that it's an indicator function which is defined on y and takes a real value. So indicator function takes the value 1 or 0. And notes that, so then if you plug this guy in, so you plug the indicator and you take compute this guy, so this is just a measure of this, and when you plug this guy in t of x with respect to t mu of x, then, just like we argued before, this is this, and these two guys are equal by our hypothesis. We assumed that mu is exactly equal to the push-forward measure of mu. So we verify, or we can say that star, so we can call this equality star. So we can say that star holds for all indicator functions. Okay, so we're good for indicator functions, and now what we need to do is prove this for simple functions, which is also trivial. So just by linearity, star also holds for phi which take the form ai1 ai, y goes from 1 to n, for instance. So it also holds for linear combinations of indicator functions. And then after this is just the density argument. You know that, so these are, of course, remember that usually they're called simple functions, right? So we know that simple functions are dense, and that means that any sort of bounded function can be uniformly approximated by a sequence of simple functions. And so notice, so this argument sort of builds in steps. You prove it for indicator functions. By linearity, you also get the property to be true for simple functions. And now for the final step, so now let's phi be a arbitrary Borel and bounded. So by Borel, I just mean that it's measurable. So Borel and bounded. Then there exists phi k, sequence of simple functions such that you can uniformly approximate phi with the sequence phi k. So what does that mean? That means that phi k minus phi, the infinite norm, goes to 0 as k goes to infinity. And thus, so now we just, plug this in our integral. And so what do? We want to compute phi of t nu, right? But this is the same as taking the limit of phi k d nu. But, and we know that phi k satisfies the integral equality, which I denoted by star. So in particular, I can change this measure to mu by just simply composing with the map T. So this satisfies this equality, and then we can push this limit inside the integral because we have bounded maps by just the dominated convergence theorem. And so then in particular you get phi composed with T nu. And so now you see that this is the same as this, which is exactly what we wanted to show. So remember, the lemma was to show that if you assumed the implication that we were showing right now was we assumed that this holds, and we wanted to show that this integral equality holds. And the way we did that was we went in steps. We first showed it to be true for integrated functions, then we showed it true for simple functions, and then finally for using the density of simple functions in the space of bounded measurable functions with the infinite norm. We just use simple dominated convergence theorem to prove this. So there's actually a very cool sort of consequence of this result, and we can state this as a corollary. So corollary, what we can say is that for all functions phi going from y to r that are Borel and bounded, what do we have? It holds that that when you integrate with respect to phi, so maybe this is, perhaps I should write like this. So when you're integrating phi with respect to the push forward measure mu, so this is the push forward measure, then this is nothing but just composing phi with t and then integrating on the space x, phi composed with t, integrating with respect to the measure mu. That's it. So the idea of so this sort of simplifies your computation. I would say that instead of working with a push forward measure, you just work with your usual measure, but you just need to compensate by composing with the function with t. And then now we can also prove something interesting. So let me change the page. What we can prove is, so let me state this as a lemma, we can in some sense establish a relationship between composition and the push forward measure. So let T be a map that goes from x to y, and then let's take another map, S, which goes from x to y. Both of these are measurable. Then if you're composing S with T and you take the push forward measure with respect to mu, then this is the same as using S and taking the push forward measure with respect to T, push forward measure with respect to mu. So it looks kind of complicated, but it's just playing with the simple idea of compositions and push forward measure. And we will just quickly prove this so that there's no mystery around this funny looking result. So how do we do this? We have to just use what we know. We know this corollary, and this is exactly what we're going to use. So remember, we want to show an equality between two measures, and the way we do that, between two push-forward measures, I would say, and the way we do that is we take a bounded measurable function, and we just integrate it, and then by some reductions, we'll show that one integral is equal to another with respect to another measure, and then we're done. So just recall this lemma that we have here. So we want to show this measure is equal to this measure, and the way we do that is when we integrate any Borel unbounded function with respect to that measure, we show that it's just the composition, and that's the idea that we'll keep in mind to prove this. So let's proceed. Let's so take phi to be a map, which oh yeah, perhaps I should change the space for this, otherwise it doesn't make sense. We have three spaces. We have x, y, and z, right? So phi is a map that goes from z to r, and then we integrate, right? So we integrate on the space z. We integrate phi with respect to the measure which is formed by the composition. So you have this. So you take this guy, you integrate with respect to this guy. But then remember, this just means that you're integrating on the space x by just composing phi with s and t. So this is just the composition with respect to this. But now notice that here, let me put a bracket. But now notice that you don't need to keep all the compositions. You can just keep s, for instance, and this phi of s is composed with t. But then this is the same as integrating on the space y with respect to the push forward measure defined on mu using the map T. And in particular, there's another composition which is not a problem, but then this is the same as integrating phi with respect to the push forward measure that is defined using this as a measure. So it's probably getting a little complicated, but yeah. So yeah, it's just playing with compositions and the lemma that we proved before. But then, so of course, because we have phi here, and we're integrating on the same space, and if this sort of inequality is holding for all phi which are bounded and measurable, then in particular the measures have to be the same. And so this implies that the composition, sort of the measure, the push forward measure with respect to the composition, can be decomposed as a sequence of two sort of push forward measures. Perhaps this is the best way to write it. Yeah. So we can do this. Okay. So now that we understand a little bit about the object, the push forward measures, we can now move to something more interesting, which is defining what does it really mean for a map to be a transport map, right? So remember, we're in the business of optimal transport, and so we need to understand really what does it mean to transport one measure to another, right? So we give a definition. This is the definition of a transport map. And so what are the ingredients, right? What do we need? Well, you want to move one measure to another, right? And so you start with a measure mu, in the probability space of x, and nu, which is in the probability space of y. You need a map, right? We're defining a map that goes from x to y, and this map is called a transport map. From mu to nu if nu is indeed a push forward measure. So if this equality holds, then T will be a transport map. And so this is what it means actually to transport a measure mu to a measure nu, right? So there's something, I guess, which you should think. So in optimal transport, what we're doing is at least one formulation. What you're trying to do is you're trying to find this transport map, right? So you're given two measures, and your goal is to find this transport map that allows you to optimally transport the measure mu to a measure nu, right? With the least cost, with some notion of cost, right? Which we can define later. And so one of the questions that you should ask yourself is that does this sort of transport map exist, right? Is it possible that I can give you maybe a combination of two measures for which there is no transport map, right? And so this is helpful later on actually to understand different formulations for optimal transport problems. So perhaps this could be like a remark. And so consider, for instance, the measure mu, which is just the Dirac mass at the point x0 for x0 that lives in the space x. And then let T be any arbitrary map, right? I've not put any constraints on it apart from the fact that it should be measurable. And we want to see that if indeed T is going to we will try to find like a property about T, and then we'll see that T if nu is not exactly what if nu is not exactly a Dirac mass also, then you won't be able to find actually a push forward measure. So perhaps it's better if I just do some computation. So the goal is that we start with nu, and we have T, and let's just compute something, right? Let's just compute something. So we look at the integral of phi with respect to the push forward measure, right? And this is nothing we know from our computations before. You just this is just the integral on x, and you just do a composition. But then remember that mu is nothing but your Dirac mass, right? And so in particular, this just evaluates the function at the point x0, and so the result is x0. And so what you can notice immediately is that the push forward measure here is nothing but a Dirac mass itself, right? It's actually so this implies that the push forward measure mu is T of x0. So it's evaluating phi at the point T of x0. So it itself is actually a Dirac mass. And so if you go back to the definition, and so if I started with a Dirac mass here, a Dirac measure here, then if nu was not a Dirac measure, then actually you would not be able to find a transport map from mu to nu. So this is this shows that it's not always possible for you to have a transport map from two measures. So this is an interesting example to keep in mind for something that I'll talk about later. So now we have this, then there's another notion that's sort of important when we discuss about transport maps. So the thing is, we notice that there's a problem with this definition, right? That uh, even that it's not always the case that, for any mu and nu, you'll be able to find the transport map. So perhaps we need a I would say, a more relaxed version of transport map, and that's called coupling or a transport plan, depending on the books that you're reading. And so let's define what a coupling is. So let's see. So definition. This is the definition of a coupling. Okay, so how do we define this? So the way we denote coupling is it's a probability measure on the product space of X and Y, right? And so gamma is a coupling of mu, which is a probability measure on X, and nu, which is a probability measure on Y, if the following holds. So what you want to do is you want to satisfy some sort of marginal log condition. So if you take the push forward, so pi of x is just a projection map. So pi of x, x of y, is simply x. And let me just write this here. Pi of x, y is simply y. So it's just a projection map. So if you take the push forward measure with respect to this projection map, then you should recover the laws. You should recover the laws mu and nu. So if you project on the x component, you should recover the law mu. And if you project on the y component, you should recover the measure nu. So if this condition holds, then gamma is said to be a coupling. And now notice that, so of course, you can state an integral version of this. What does it mean for gamma to be a coupling? Well, this just means that, if you take a bounded function phi of x, and I probably should connect this here. Yeah. Okay. So if you are integrating on the product space with respect to the measure gamma, so x of y, then this is just simply saying that this should be the same as integrating x on the space t mu of x, right? So of course so maybe perhaps I should proceed in steps. So gamma is what? Okay, maybe I skipped a step here. So gamma is what? Well, gamma is the push forward measure using the map pi of x, right? So when I'm integrating with respect to gamma, well, this is the same as saying that I'm integrating with respect to phi composed with pi of x gamma. So if I put xy here, perhaps it's not clear. So it's a very simple argument actually. So t gamma. So pi of x of x comma y will give you the value x, and that's what you feed into phi. So that's why it's phi of x. So there's nothing but just transforming this to this. But then notice that this composition should remind you of something related to the push forward measure. In particular, this is nothing but this quantity here actually, right? You're composing phi with pi of x, and you're integrating with respect to gamma, but this is the same as actually integrating on the space x with respect to the measure mu, right? And you can do the same for phi y, for instance. So if you're integrating on perhaps like this, then this is the same as integrating phi of y with respect to the measure nu on the space y, right? Just by similar argument. Okay. So what can we do now? Well, in particular, I guess it's useful to observe that that you're able to always find a coupling. So, given any two probability measures, you're always able to find the gamma, uh, at least one gamma, if not the most optimal one, but at least the set of gamma given mu and nu is not empty, unlike the case for transport maps here. So that's good news. And why is that the case? Well, you just take the product measure, right? So so given mu and nu, so we denote capital gamma to be the set of all couplings on mu and nu. Then I claim that at least the product measure belongs to gamma of nu of mu. And why is that the case? Well, it's pretty simple. What you have to do is just observe that that if you're integrating respect to phi of x, then it's the same as integrating respect to this, because so here I've taken gamma as the product measure, and the product measure decomposes, right? So when you're integrating phi of x with respect to gamma, it's exactly integrating phi of x with respect to the measure mu of x times the measure nu of y. And so here it's simple. So you can take out the y term first because that's independent, and then you have the x term to take care of. So you have phi of x d mu x, and now this guy is just 1. So then this is just phi of x d of x. And you can do the same argument for integrating the function with respect to y, right? And so this at least convinces you that there should be at least one coupling and that this set is not empty. So that's good news. Yeah. And so just a last remark to end this discussion, which is also useful, is to observe a relation between couplings and transport maps, right? So we defined these two ideas, and it's always good to sort of understand how they're related to each other. So let me do this on another page. Perhaps I need to. So how are they related? So the objects of interest are T, which is a map, which is, let's say, our transport map. And so in particular, it will satisfy this condition. Of course, we're given mu and nu as to probability measures. And so then what you can do is you can define, consider gamma of T, which is defined as follows. So gamma of T is this measure, is a product measure defined as follows. So you take mu, and then you take this map, which is identity times T. And so maybe perhaps I should make it a little more clear. So identity cross T is a map that takes a value in X and gives me a value in the product space. In particular, it will take a value x and assign me a value x, t of x. So if you consider this map and you take the push forward measure with respect to mu, then this is indeed a probability measure in the product space. That's the first thing which you can observe, and then lastly, you can observe that that it indeed lives in the set. So lastly, note that gamma of t belongs to as, so perhaps I make this clear. So the way we check that it indeed lives there is by looking at the push forward measure of the projection. So you take this guy, you take the push forward measure with respect to gamma of t, and what is this? So this is pi of x, push forward, and what is gamma of t? It's the identity cross t, which itself again is a push forward measure. And now we have to use our results. So you have two push forward measures. So perhaps I go up and recall the identity that we'll use. It's perhaps here, yeah. So we have S push forward, T push forward. Well, it's just nothing. You just compose these two guys and it's the combined push forward measure, right? So that's what we use here. So push forward, we combine these two guys. So the projection composed with the map, when you take the push forward of this guy, and well, this is nothing but just the identity, right? Because you just take the first component. So when you project on the first component, you get the identity, which is just you get identity push forward mu, and well, this is nothing but this is just mu, right? And because yeah, we can check this very quickly. So identity push forward mu of A is nothing but identity inverse of A, but then the inverse of A is just A, so it's just mu of A. So this is exactly mu. And then, you know, you can just do the same argument by the same argument. You get that when you project with respect to the variable y, and you take the push forward of gamma of t, well, it's just nothing but actually nu itself. You just follow the same argument. You just replace x with y everywhere, and what you will notice is that in this step, when you're projecting instead of x on y, you will get t. So you'll get t push forward mu, and that's nu by definition, right? We assumed that t was a transport plan, right? We assumed it. So if you're given a transport plan, then you can easily come up with a coupling, and this is a canonical way to define a coupling. Yeah. So yeah, that's it for this.